Why doesn't a spacecraft burn up when it hits the atmosphere at Mach 25, when the air in front of it turns into glowing plasma? Because the heat shield is designed to sacrifice itself. It doesn't just block heat, it absorbs it, breaks down on purpose, and carries energy away as material burns, chars, and flakes off. Like how a candle's wax melts and protects what's underneath, an ablative shield lets the outside take the punishment so the crew inside stays cool. First, a correction. Reentry heating isn't mainly rubbing like sandpaper. The big heat source is compression. The spacecraft slams into air so fast that the air can't move out of the way gently, so it piles up, compresses, and heats into a glowing shock layer. That super hot gas then tries to dump energy into the vehicle by convection and radiation. Most heat attacks the stagnation point, the spot where airflow basically stops and pressure peaks. That's why capsules have blunt shapes. Blunt bodies push the shockwave outward, creating a thicker cushion of hot gas so the worst heating happens in the air in front of the craft, not inside the metal. Now the magic, ablation. Many heat shields are made from a resin-soaked, porous material. As heat soaks in, the resin chemically decomposes, that's pyrolysis, soaking up energy. It leaves behind a tough char layer that's a great insulator. And the gases released during decomposition blow outward, like a tiny protective wind, pushing hot plasma away from the surface. Here's the key idea: the shield doesn't need to win against heat forever. It only has to survive long enough. Every bit of material that cracks, flakes, or vaporizes steals heat from the vehicle, because phase changes and chemical reactions consume energy. And when that hot material leaves, it takes the energy with it. The spacecraft is literally throwing heat overboard. Not all shields work the same way. Ablatives are like single-use armor, simple and extremely reliable for high-energy entries. Reusable systems, like insulating tiles, aim to survive without losing material, but they demand careful maintenance and have different weak points. Designers pick the strategy based on mission, speed, heating, weight, and how many times you need to fly. Heat shields aren't chosen in isolation. Trajectory is part of the shield. A steeper entry dumps energy fast, brutal heating over a short time. A shallower entry spreads heating out longer, which can still be dangerous because you cook for more seconds. Speed matters too. A small increase in velocity can mean a big jump in heating. So guidance, angle of attack, and timing are as important as materials. Engineers track heat flux, surface temperature, how fast the char front moves, and how much material is lost. The goal is simple: keep the structure and crew compartment below safe limits with margin, because in re-entry, almost enough is the same as failure. So a heat shield survives by not trying to stay perfect. It survives by changing, charring, venting gas, and shedding heat like a controlled burn. Now your turn. Why do you think most crew capsules are blunt and round instead of sharp and pointy?